Foundation, Impact, Tutors, Fit, School of Engineering, 200 level, Thermodynamics, Part 2. The course outline for this video include summary on heat and work, sign convention for calculation, and calculations on heat and work. Heat and work summary. Take note of the following summary on heat and work. Number 1, heat and work are path functions. They depend on the path, while properties like temperature and pressure are point functions. Okay. Number 2, point functions are exact functions, while path functions are inexact functions. Number 3, heat and work are boundary phenomena. They always occur at the boundary and not system phenomena. They don't enter the system. Finally, number 4, heat and work are transient forms of energy. They depend on what is happening on the surrounding. Now, sign convention. We have two sign conventions, by objective and by direction. Okay, but in this video we'll be using by objective for our calculation. Take note of that. So by objective, if Q is positive, it means heat is supplied to the system from the surrounding. If Q is negative, means heat is supplied from the system to the surrounding. Okay, if W is negative, it means work is done on the system by the surrounding. Then if W is positive, it means work is done on the surrounding by the system. By direction, both work and heat going in is positive, and then both work and heat coming out is negative. So Q is positive when heat is supplied to the system. Q is negative when it is given out to the surrounding, while W is positive when going in and W is negative when coming out. Okay. Calculation. Example 1. In this video, we'll be looking at example 1. The mass of an ideal gas is enclosed in a piston cylinder arrangement. The gas is compressed reversibly in such a manner that the pressure and volume are related by the expression PV raised to power n equals to constant equals to K, where n is equals to 1.4. If the initial pressure and the volume of the gas are 100 kilonewton per meter square and 1 meter cube respectively, and the final volume is 0.25 meter cube, determine A, the final pressure of the gas, and then B, the work done during the process. Let's begin. First, we use diagram to picture the question. We use a P V diagram. Now, two values will give us a point. So we are given 100 kilonewton and 1 meter cube as the first 2 points. That gives us the first point. Then the second point, P2 and V2 0.25 meter cube will give us the second point. So the line joining the 2 points is known as the process 1 to 2. All right. So it's the arrow is pointing up because there's compression. If it is expanding, it will be pointing downwards. Take note, the volume is reducing. Solution. First, we need to know what we are given. We are given P1, 100 kilonewton per meter square. Kilo means 10 to the power 3, so 100 times 10 to the power 3 Newton per meter square. V1, 1 meter cube. V2, 0.25 meter cube. Then we are given a law, PV raised to the power n equals constant. Required, what are we looking for? We're looking for P2, the second pressure, and the work in that process. So using PV raised to the power n equals K, we have P1 V1 raised to the power n and P2 V2 raised to the power n. If we make P2 the subject, we can find the value of P2. All right. If we substitute the values for P1, V1, P2, V2, and n, we have 100 times 1 raised to the power 1.4 equals P2 times 0.25 raised to the power 1.4. Right, don't forget n is 1.4. So 100 times 1 raised to the power 1.4 give us 100. Cos P2 times 0.1436. Use your calculator. If we make P2 the subject, we're going to have 100 over 0.1436. When we divide, you can use your calculator to confirm this. P2 will be given to us as 696.38 kilonewton per meter square. B part of the question, work done in the process. To calculate the work done, we use W12 equals integral PDV from volume 1 to volume 2. So we'll be using the values for the volumes to substitute as we go on. But P, V raised to the power n, is equals to constant, right? That's the condition we are given. If we make P the subject, we're going to have P equals K over V raised to the power n. We're going to substitute these values inside the work equation. Substituting inside the work formula, we're going to have W12 equals integral K over V raised to the power n dV. Next, we'll bring the K out of the integral sign. Don't forget from 1 to 2, okay? So if we bring K out, we're going to have K integral 1 over V raised to the power n dV from process 1 to 2. At this point, we're going to apply indices. The V raised to the power n will go up if you apply indices, and it will be negative now. So we're going to have K integral V raised to the power minus n dV. So we're going to integrate V raised to the power minus n dV. Don't forget our volumes are 1 meter cube and 0.25 meter cube. Let's substitute it at this point. So if we're integrating, we're going to have K outside. If you integrate V raised to the power minus n, you have V raised to the power minus n plus 1 all over minus n plus 1. Our limit from 1 to 0.25 will follow us. So if I arrange the power, minus n plus 1 can also be written as v raised to power 1 minus n all over 1 minus n from 1 to 0.25. Is that okay? At this point, we need to find the value of k before we can continue. Now remember, p v raised to power n equals to k, so we can use that to find the value of k. So we know the value of P1, we know the value of V1, we know the value of N. P1 is 100, V1 is 1, N is 1.4. So when we simplify this, we're going to have 100 kilonewton per meter cube for K. So we substitute the value of K, which is 100, all right? 100 kilonewton per meter cube from our limit 1 to 0.25. So at this point, we're going to put the value of 0.25, then the value of 1 into the equation. So when you put 0.25, you have 0.25 raised to power 1 minus 1.4, n is 1.4, all over 1 minus 1.4, minus the same thing, 1 all over raised to power 1 minus 1.4, all over 1 minus 1.4. All right? When you simplify each of the smaller brackets, we're going to have 100 into 0.25 raised to power minus 0.4, because 1 minus 1.4 will give us minus 0.4 all over minus 0.4. The same thing goes for the other bracket. Now when we use calculator to simplify, if you simplify 0.25 raised to power minus 0.4 all over minus 0.4, you have minus 4.3527, and the other bracket gives us 2.5. Okay, so when you add the value inside the bracket, you have 100 into minus 1.8527. Multiply with 100, we're going to have W12 as minus 185.27 kilojoule. The negative sign simply means work is done on the system by the surrounding. Exercise. You're going to do the following exercise. Take time, study the example again and again, understand it properly, and then you can do the exercise for better understanding. Is that okay? In this exercise, you have a law PV raised over n equals to k, where n is equals to 1.2. The initial pressure and volume you are given as 120 kilonewton per meter square and 1.5 meter cube, respectively, and the final volume as 0.36 meter cube. Right? You're going to be determining the final pressure of the system, and then you're also going to be looking for the work done in the process. Next exercise, you need most of a fluid at a pressure of 3 bar with a specific volume of 0.18 meter cube per kilogram contained in a cylinder. You are given a law P equals C over V square, which you are going to obey. You have to calculate the work done during the process. Also, question number 3, you have an initial volume of 0.05 meter cube of a gas at 6.9 bar. It expands reversibly. Remember, this one expands, so the arrow will be pointing down when you are drawing the diagram. The law is PV raised to power n equals constant, okay, until the volume becomes 0.08. So the volume is, when it is expanding, the volume will increase. When it is contracting, it will decrease. Calculate the work done also, and sketch the process on the PV diagram. All right, for more of our video, ensure you subscribe to this our channel. Okay, thanks for being a part of this class.